when we need to go over this, the clock system extension performance considerations. Okay? So assuming that you do complete your clock library, which you should. If you haven't completed, it should be completed by the end of this weekend, right? Because we're moving forward. In fact, the demo I have now is already using the library. Maybe I should bring up the demo and show it to you. Okay, so this is this? Well, let's just go here and then. So the demo that we did was clock demo 1. So now I created clock demo 2, which is exactly the same thing, but now it's using the library. Okay. So so this is the way it will look like.
Hey, John Costa.
We basically set up the clock to 40 megahertz with this function. Okay? Now, one interesting thing is that some things that I mentioned yesterday, that if you notice here, I am outputting the clock speed before the clock init and after. Okay? Oh, and I need to correct my word, of course.
Everything is connected, hooked up to this guy, so hopefully I don't.
You want to borrow mine? Are you good?
Right, I'm good, thank you. I was working on the display that we're gonna use with 2250 to get working hopefully today, but it's still.
You can do that in your sleep.
Yep, kind of.
Okay, so again. So once I flash this thing, you will notice that it sends two messages, one with the clock speed at 16 megahertz, and the second one with the clock speed at 40 megahertz, see, after initializing the clock. Yep.
I actually noticed when I was doing testing for the library that it wasn't in fact updating the core
Yes.
clock speed. So we had to actually call a system core
Yes.
clock update
That's,
function.
that's exactly where I'm going with this.
Sorry.
You should add that at the very end of your clock init. In fact, for the purpose of testing this, if I go to my clock library, see, and I comment out this system core clock update, I'm not zooming into this because I want to move it, like show it like very briefly, and I rerun this. That is exactly what's happening now. See, it's showing 16 and 16. It's not updated. Okay? It's not updated because I removed that. But of course, to prove that even more, I could call it here, right after the clock. And that function does update that library. I mean that variable, okay? So it is important that you have this function call inside your clock init PLL at the very end. So you can properly keep track of the system core clock variable, and that can be used with what's coming, with the timing, with everything, because all the peripherals need to know what is the actual clock speed. All right? Now, what happens, because I have the USART somewhere here, okay? In this user init, when I do the baud rate, of course, is being using also the system core clock variable, right? Now, on purpose, what I did with the other section was to put the clock speed init after the user. Here, for example.
Interesting.
Where is the clock init, the user? Oh, it's here. Okay, never mind. So let's not put it too far away. Let's put it right after the user here. What do you think is going to happen if I do that? Moreover, I'm gonna send, this is hello world 2. I'm gonna send a hello world 1 before the clock turns. Okay, let's run this again.
I mean, you should see it.
Let's pay attention to the terminal, it's on the other screen.
Print out the original update.
Hello world 1, that goes correctly, and then the second one I see garbage. Can anybody except Om explain to me why is this happening? Nothing personal, Om, because you were in the other class, right? So you know the answer.
So,
Oh, you were also, yeah.
Don't know what was it?
so both of the baud rates are the same,
The baud rate is the same,
are they?
are they?
Well, I don't know, I'd have to take a look at your code
Yeah.
and see. Because if there's a
So,
baud rate mismatch.
The
then-
sequence in how we do things in embedded systems is so important. So when we start running our system, and if we don't do anything to the clock is gonna run at
16.
60 megahertz, taking the speed from the HSI, right? Then, after initializing all these peripherals, I'm going to initialize my USART that is gonna use system core clock, 60 megahertz, and it's going to calculate the baud rate, and it's gonna store it, and it's gonna configure the USART. It's gonna work fine here. However, then later, I come and I change the clock speed, then my USART is no longer at 9600 baud rate, because I changed the clock. So whatever calculation I did will have to be recalculated and reinitialized. In fact, if I reinitialize the UART right after the clock, again, you will notice that now both work. There we go. Let me just clear the screen. The interesting thing though is like, it's not doing the backslash. Yeah, it's kind of strange that it's not. Why? It's kind of not jumping to the other line. Is it because of the? It's backslash R backslash F. Oh, something is strange. Oh. Yeah, I'm a bit confused, to be honest. But anyways, let's not get hung up on that too much because that's not what we're trying to look after here. So, in simple terms, what I'm trying to demonstrate here is that once I initialize the USART, it configures a register for the timing based on the current clock speed. Then after that, I decide to change the clock speed. Those timing settings are no longer valid. Is that clear or not?
So if we're changing the clock speed, we have to make sure to reinitialize UART at the correct baud rate.
Well, that's the patch that I did now to make it work. But what would be the best practice?
Don't change the clock speed in the middle of
Yeah,
an instruction,
configure the clock speed at the beginning, right?
unless you're going into low power mode or something.
Yeah, so maybe here, right? Because these things won't get affected, right? This is just connecting peripherals to the clock. So as soon as possible, initialize the clock. All right? And then everything else, because everything else that uses the clock, you will have already the valid speed for the clock. Okay, so everything will work fine. Now, why is it doing that? That kind of annoys me. Why is it not jumping to the other line? It jumps on the hello world 2, but not on the hello world 1. What am I doing different?
Just to make sure that's not the email that when we change your print methods down settings.
No, I don't think so. No, because we're not doing. Yeah, it could be the bar rate that is. What if I change it? Oh, because it's initializing again here. No, I don't need to initialize again.
Oh, you mean just like,
Oh, look at that. It was because it was being reinitialized. Interesting. That's very strange. Okay, anyways, so now both work. Is that clear? The clocks should be initialized at the very first, okay? All right, now I have enabled my clock output. Unfortunately, there's a problem with this scope that I have here that for some reason is not running the way it's supposed to, okay? But you're gonna test this yourself. Once you have your clock enabled, let's put this here. Enable clock outputs. Once you code all the different clock configurations that you're going to code, you're going to enable the clock output to check that with the scope, okay? And that gets done with this function. Well, once it's already coded, okay? And so far, I was dividing by 4 to see 10 megahertz on the scope, right? That's what I had till last class. But also, aside from this, I need this guy, right? Yes or not?
yeah.
Yeah, so I need to enable the MCO, the alternate function for it, right? Okay. So enabling the clock output involves 2 steps. One step is to enable to set up the proper alternate function to show it on the pin, okay? And second is to enable the clock output with this function, with a proper divider. Now, I cannot demonstrate this. Again, you're gonna have to place it on your scope. Once you run this demo, and if you go and change this DIP 4 to DIP 1, basically just to show the 40 megahertz on the scope, most likely you're not going to be able to see any signal, okay? And these scopes can handle up to 70, okay? So then what is the problem? Why cannot you see the signal? Well, that's what I'm going to explain now with this lesson, okay? Any questions up to this point? All right, so there are some performance considerations to make when we change the clock speed, okay? So by the end of this, and we went through this briefly, but too quickly last time. So we're gonna go now over it properly. So we're going to identify what considerations to make when running the clock at speeds that are higher than 24 megahertz. We're going to describe what the instruction prefetch means. And we're going to learn how to configure the GPIO speed settings so you can actually, the pin itself can handle higher frequencies, okay? The reason why you won't be able to see the 40 megahertz is not a limitation of the scope, because they can go up to 70, it's a limitation of the pin, and we're gonna change that. We're gonna have to also apply some performance tuning techniques to optimize how this thing runs at a higher clock speed, okay? By the way, why do we have all this clock system and stuff? Why don't we just make the micro run at the maximum speed all the time and we forget about everything?
It's completely dependent on the application that you're using the microcontroller for.
Yeah. For example, think about your vehicle, your DAS vehicle. The key fob has a microcontroller inside, a little tiny one. Do you think that micro is running at 40 megahertz even?
Heck no.
No, probably. I will estimate that it's not running at more than 1 megahertz, if not less, because it doesn't need to run that fast. So if it runs too fast, it's going to consume too much power, and you want that to last because it's using a coin cell battery, right? So you want it to be efficient and low power. So anything that involves speeds implies more power consumption. That is why all these pins are by default set to low speed, and we're gonna find that out. Anyways, the first thing that I want to talk about is the flash latency. Whenever you're running the clock at a speed higher than 24 megahertz, it becomes too fast for the flash memory. So it will try to fetch instructions and to actually pull data from the flash memory too quickly, and the flash won't be able to keep up. So in order to do that properly, you may not notice this problem, but eventually will come up to a performance issue. So there's a table from the datasheet, I think, or the reference manual, that basically tells you that whenever you're running the clock speed, it also depends on the core range or whatever, but more or less when you're running at 24 megahertz or less, you don't need to delay anything. But when you're running between here and 48, then you need to add one wait cycle to the flash. And when you're running at 64 or more, which is 64 is the maximum here, then you need to add 2 wait cycles. And wait cycles are basically adding cycles, idle cycles there before you can access the flash memory. And that happens in the chapter 3, where we have an entire chapter dedicated to the flash. There's a lot that we can learn about the flash, but we're not going to study the flash memory in this course. We're just going to worry about this thing. So by default, this latency field here is set to 0, 0, 0, which means 0 wait states. And then we can change this bit to set it to 1 state or 2 wait states.
So when you're actually reading the data off of the flash memory, I assume you're not going to just put in one of these wait states. You're going to test it first, see what outputs, and then if for some reason there was some garbage towards the end of the string that you were pulling from there, at that point you would then implement one of these wait states to see.
Or no, once you implement this wait state, it functions like that all the time. It will slow down for everything that it does.
Yeah, I'm just wondering, would you implement it immediately as like a safety, or would you do some testing first and then?
Good question. Yeah, so in simple terms, I got similar question in the other section. I would say for simplifying this thing, maybe just do 0 wait states, and whenever you're changing the clock to higher than 24, just do 2 wait states. So you don't have to be doing so much. Yeah. But if you want to fine tune it, of course, it's up to you, but I usually jump between 0 wait state and 2 wait states. That's it. And here are examples on how to set 1 wait state or 2 wait states. Okay? It's in my demo already. Now, somebody could already feel disappointed because you say, hey, you're slowing down the micro just to be able to access the flash. That is not good. Well, there's some compensation that can be done, and that is the instruction prefetch and cache. So basically, it's about before I can actually send the instruction to the flash, it could be prefetched. So it could be ready, loaded before, so it can go faster. Actually, this will compensate some of the time that is lost in there. So normally when we do this, we also enable instruction prefetch, okay, to compensate. And that gets done in some other register, well, the same register actually, of the flash, ACR. And we have to set this bit. That's all it is. So it's basically 2 things. One is to set the wait states and enable instruction prefetch. Done. Any questions? I know I could spend another week talking about this, but all you need to know for now is just we need to do these 2 things, right? There's an entire chapter about the flash and things such as, like, for example, if you were to create your own bootloader to flash a binary, then you would access the flash and write the flash. Then you could partition the flash to have 2 different firmwares. We could be talking about this for the entire semester, but that's not going to be the focus of this course, okay? Just so you know. So those 2 things. The other number 2 consideration is the GPIO speed settings.
Just in terms of the prefetch, sorry, there's so many questions. So that prefetch, is that automatically just prefetching the information for us? Is it also caching, or are we having to, of course, tell it, hey, once you fetched it, do instruction cache, or fetch, cache, then instruction?
The instruction prefetching is actually doing the whole process.
Awesome.
Yeah. So it's doing the whole thing in the background for us.
Okay.
for the code actually. Okay, so the GPIO speeds, if in case you haven't noticed, in the library there's some other functions that we haven't touched yet. One of them is to set the speed of the pin. And that happens in this register, in the OS speed. It's very similar to the motor register. See, it uses 2 bits and it's 2 bits per pin, blah, blah, blah. And by default, the OS speed is set to 0, which is very low speed. So all the pins are very low speed. So we can change it to low, high, or very high. I've tested, and I believe that setting it to high is good enough for all the frequencies that we're gonna do with the different PLL frequencies that we're gonna get. Okay? Now, I got the question yesterday. Why is it so complicated? Why? Well, I always get that question. But then the second question was like a follow-up. Why is this thing like, don't they just set it to upfront to very high speed and that's it, and we don't have to deal with any of this? Well, I guess the answer is the same to the previous question, right? Power. Why would you set up every single pin to high speed? If you don't need to, then you will spend more power. Right? And you have to understand, there's a table here that is actually not that quite accurate, to be honest. Because it depends, this table, it kind of implies information from here, but it depends a lot on the voltage that the micro is working at, so it's not that accurate. We proved, right, that without modifying anything, we were able to see a 10 megahertz signal on the scope with no issues, remember? We set it to 40 megahertz, we divided by 4, and everyone that tried this was seeing the 10 megahertz. So it looks like the low speed is not, it says approximately 2, but it can go up to 10, more or less. Okay, so this is not that accurate. But then the moment that we jump to somewhere around 40, 50, we want to use high speed. So I'm going to say maybe we're going to jump between nothing, meaning low speed, and high speed. Okay? And in which cases we may want to have a pin set to high speed? Well, obviously to output the clock at full speed. And in some other cases, like other type of communications that we're going to learn later, like SPI or any other protocol that goes really fast. But if I'm going to ask you to toggle an LED, so from what you've seen already, like in the exam, you're probably toggling at 2 kilohertz, 5 kilohertz, 10 kilohertz max, no more than that. So for most things that we're going to do in this course, low speed is going to be good enough. We're only going to have to set up this when we're using something really high speed, which is in this particular case. Okay? So that keep in mind. And these have to do with the formula that is kind of complicated, but basically, what I want to stress the fact here that when you talk about square signal and you have your pin toggling, you have to understand that if you were able to zoom into this signal, you will really see this. Something like that, right? Where you will have a rising time and a falling time. The signals in reality are not perfect. They're not perfectly square. There's a slope. You just don't see it. But when does this become more relevant? When you are at higher speeds. Okay? That is why we need to do all this thing. And you will see some of these too in other hardware courses when you study, like maybe in semiconductors, when you get to that part with the op amps, and then you talk about the slew rate and all that kind of stuff. Has to do with the same thing. And how fast is the silicon able to keep up with the time? Okay?
Not very well in an op amp.
Yeah, no, it's terrible. It's slew rate is your enemy. Anyways, so we go into this register, and for example, to set the GPIO to high speed, we do the same thing, 2 times the pin, and then we will bishop by that, the number 2, which is high speed. If we wanted to do very high speed, then we need to do a 3, right? And of course, to clear the settings, we're going to do the inverse mask of the 3 to clear the proper settings. So basically, what I did in this demo here, I changed this. See, this is what you want to do for testing. I'm gonna give you this demo because you're gonna have to test it because I cannot demonstrate it on this scope. Because it's broken. I gotta update the firmware. I just didn't have a flash drive or something to do it. I tried to do it with a hard drive and it didn't work.
No.
Yeah. Somebody messed up with the firmware of this scope and now it's broken. Yeah. Just to have that Enterprise, Star Trek Enterprise screensaver, and now it broke the scope. I'm pretty sure that was the case. Anyways, so I'm gonna have this one commented out, okay? So what you're gonna do is you're gonna test first with division by 4. You should be able to see the 10 megahertz once you code your library or you finish coding it. And then you uncomment the divide, comment this other one out, and you divide by 1, and you see if you can see the 40 megahertz signal. But that's going to depend on this. Oh, sorry, and the flash latency correction is right here. We're gonna do that in just a moment. So, we're gonna set the PA8 to high speed. PA8, which is actually the pin that we're using for the clock output, right? And the way we do that, we go into the speed register, we clear it with the mask, and I'm doing it with this, so you can remember how to put this in your library, because you should be able to code this in your library. If you have any questions, you can ask Om. I'm pretty sure he already coded it, right? Did you? Yeah, see? It's not hard. It's the same as the motor, right? And then after that, we're gonna set 10, which sets it to high speed. You're gonna play with commenting and uncommenting this thing, and you will see that it makes a difference. Once you have it set up to send a signal of 40 megahertz out of the pin, if you don't have these lines, you won't be able to see the signal on the scope. But if you add these lines, you will be able to see them, because now you set the pin to high speed, right? And as for the flash latency, there's no actual way you could test that it's working or not, to be honest. Not that I can think of right now. You just have to trust the process, right?
You have to remove latency.
Yeah, and the way I do this, I just go into that register that it shows in the lesson. I clear the latency settings with this mask, and then I do _1, which is 2 wait states, and then I enable pre-structured prefetch. So most likely you want to add this maybe to your clock library. You decide where to add all that, because the moment that we add more things, then it becomes a bit more convoluted if we miss one of those, right? So maybe you want to have this at least into your library. So whenever you enable the PLL to higher frequency, then you put this. And as for this one, you could build it into your clock if you want, but the problem is that the MCO line could be like 3 different pins. It could be in PA8, PA9, or yeah. So then how are you gonna do that? I don't know. That's when you have to do decisions. You have to make decisions about how you implement it. All right. Any questions up to this point? Yeah.
In terms of actually placing that flash latency correction into the library specifically, could we just set up like an enum structure specifically for the different latencies, or would it just be easier to?
Well, you could actually. I was thinking about that. When you look at the enum for the clock, I thought about this because I thought for some reason I was gonna get the question. See, mine is not fully completed, but once you populate all I mean, I have it, but it's just in a different repo. I'm not sure if once you put these numbers, actually these numbers increment in sequence. So whatever the number comes up here ends up being bigger than this one. I'm not so sure because it depends on the location, right? I guess the safest way you could do this is do like a switch case, but then put like when you have case 1, case 2, case 3 together, and they do the same thing. You could do, if the case is this, or any of this, set it to high, apply the latency, whatever. Or maybe it would be better to do it here, right? I mean, if it's any of these 3 cases, do not apply it. Otherwise, yeah, I don't know. Maybe with a NIF else? Yeah, If the PL, yeah, that could do it, right? If PLL range is different than this one and this one and this one, then apply it. I guess the if else works better than the judge case.
Just do 3 ifs.
Yeah, but you're testing 3 conditions, right? If it's different than this one, and different than this one, and different than this one, that means that is some of this one.
Right, but we've got these clock ranges that work specifically with that speed.
Mhm.
So then why couldn't we just have it set up to, if it's within this range, we know that this speed works, so then set it to this speed, and then within the middle range, we have medium and, or, high, and then, above at 64, that would probably be the only one we'd set it for high speed, right?
No, actually, high speed it will start from. Oh, for prefetch it starts before at 24. Yeah, but for the GPIO pin it starts around here, 32, I think.
Okay.
Yeah, I guess that has to be hard coded for the GPIO, to be honest. And it's not that I'm going to ask you every time to have the clock outputs, okay? But because it's just a testing procedure, right? Every micro should have a pin at least to output the clock, because that's the way it works. You do not set the clocks to a certain speed and then just hope that it works. It doesn't work like that. You need to verify it. So the way of verifying it is actually outputting the clock on a pin. Although we do have a software way of verifying it, right, with the CMCs that we do. But to be 100% reliable in our assessments, we need to scope it. That's why we have all this equipment, okay? And yeah, and that's why using the equipment is so important, because I cannot picture in my brain an embedded system developer that doesn't know how to use a scope properly, to be honest. So if you wanna get into this field at some point, you gotta get proficient with the scope tools and logic analyzer. And that can be learned through time and practice. Don't worry too much if you're not considering yourself that proficient. All right, so like I said, I'm not going to be able to test this thing here, but what I'm going to test is that I am setting my clock to 40 megahertz, and then I'm using this delay milliseconds function that I've been using for quite a long time, and I'm going to use my delay 1 millisecond to toggle my PA5, right? My user LED, which is, I'm assuming this guy here. Okay, yeah, that's correct. Let me just trigger this properly and show the measurements. And we're going to add positive width. Okay, so delay 100 milliseconds, perfect, perfect. I'm going to test this thing, bring up the scope, and what happens? Who can tell me? Not on, please. I'm just kidding, no. No, don't take it personal.
Okay.
Why is not 100 milliseconds?
Oh, our calculation for this delay is specifically based off of 16 megahertz,
16 megahertz.
not 40.
So how many times faster is this than the 100 milliseconds? Well, it's a simple calculation, right?
It's like 2.8x.
It's 2.5 actually. If you do 100 divided by 40, it's 2.5. So it's 2.5 times faster. If we multiply this by 16, gives me 40. Makes sense or not? The clock is 2.5 times faster.
So that delay needs to be 2.5 times larger.
Yeah. Now, are we going to tweak our functions to accomplish that?
Can?
You could, as a good exercise. Am I going to do it? No. Why? Because sooner than later, we're going to discuss the timer, where we're going to have accurate timing. So why even bothering? Like, we're not going to do these delays based on cycles anymore. We're just going to use timers from when we start using a timer. So this is an intuitive approach to get a delay to show you about the cycles and all that, but beyond this, timers. What it is important though, is that the timer knows what the clock speed is. And in order to know what the clock speed is, that is why these guys have the system core clock, and that needs to be calling that function to update it properly. You know what? I was teaching the old micro, and probably some of the ones that took it remember. At least I did it in my section. We had to keep in the clock library, keep track in a variable ourselves to keep track of the clock. And every time we would change the clock, we'll update our variable, right? But we were doing that manually. Now this thing is being done for you in the background, but the only thing you need to do, you need to call this system core clock update, right? That doesn't need to be here anymore because I have it in my library. Yeah, so this practice is typical, okay? So it's better to do this. Some other approach, some alternative to that would be like anytime you initialize a peripheral, you pass in the clock speed, which I find, honestly, not a big fan of it. Like if you had to initialize your UART, for example, to a certain baud rate, so let's say, where is the UART in here? You also have to add an extra parameter that sends the clock speed, which I find it unnecessary because the user library in the background can actually call that library, that variable, and know what the clock speed is, as long as you update it, okay? Any questions? With this, we close the chapter of the clock, and it's going to be an assignment coming this weekend. But in the meantime, you guys kind of wrap up the other pending assignments. And yeah, and so by Monday, I will probably have the assignment for the clock, which most likely what I'm going to ask you to do, to be honest, is to change the clock in runtime, which is something that I will probably won't ask you to do ever anymore after that. So which means your functions have to be robust. Probably you're going to have to scroll through through an array or something like that with a couple of buttons and then change the clock speed and show me what the clock speed is. Maybe using a printf. I'm not going to ask you to use a USART because then you're going to have to reinitialize the USART every time. So maybe just with the printf, it's good enough. That's what I'm thinking for the clock. And also outputting the clock, having the clock output on the pin, checking that, and things like that. Check out?
No.
Oh, problem. Okay. Yeah. Okay, so that's it then. So we're